Alright guys, we're going to talk about continuity right now. And so what does it mean for a function to be continuous? Well, a function would have to satisfy the next three conditions. Firstly, well, we're going to analyze a continuity at a point x equals c, and we say that the function f is continuous if firstly we need the function to be defined at c. So in the previous examples, in the previous sections where we had that f was not defined at a point, then that function immediately is not continuous at that point. So that's the first thing we need. Then we need the limit of the function to exist as x goes to c. So if it doesn't exist, for example, that function where we had something going on like this, that there was a jump, those kinds of functions are already not continuous. So we need the limit to exist. Now, it went a little high. For some reason it scrolled. Sorry about that. But okay, so we need the limit to exist. Then the third thing we need is that the limit should exist. Should the limit exist, it has to be equal to the function at that point. So let's take a look how that could fail. For example, we could have the limit existing, so that means the function, as it's going to a certain point, the limit does exist, but then the function is defined to be something else. You don't want to call this continuous because you had to jump out of the graph to draw it. So essentially, or roughly, a function is continuous if you could draw it without lifting your pen. I don't know why this is doing that jumping. I'm sorry about that. But anyway, so let's see. If we're given this piecewise defined function represented by this graph, so say the blue is the left side, to the left of x equals 1, that seems to be our value of c. So as x comes to c from the left, it's f of x is going to this point right here. It looks like a 1 as well. And where you're coming from the left, you're also going to the same 1. So the limit, it seems like the limit, let's call this function f, it seems to be equals to 1. Is the function defined there? Well, there's not a hole, so we assume the function is defined, and the function, in fact, is equal to 1. So since the function and the limit match, then we say the function is continuous. So therefore, f is continuous. And now if I would just leave it at that, I would be wrong, because our analysis was based at the point x equals 1. So at x equals 1. So that is to say, continuity is a local property. So always we're going to be talking about continuity at a certain point or at an interval. We're not going to talk about continuity just in the vacuum. If you just say the function is continuous, what you really mean is the function is continuous on every point of the real line. So let's look at a different function like this one, for example. When x goes to 1, let's look at the continuity of this function. So let's call this c equals to 1. So is the function defined? Yes. The function at 1 takes this value right here, the solid dot, and that is going to be equal to 1. Now, does the limit exist? Okay. Alright, so somebody came and knocked on my door, I guess. So, where was I? Yes, the function at 1 is 1. Now, the limit, that's where we were. Well, limit from the left seems to be going to 1. So as x goes to 1 from the left, that's why I put a negative. That is going to 1, but then we look at the limit from the right as x goes to 1. And the limit as x goes to 1 from the right is not equal to 1. It's actually equal, looks like -3. Since these two guys are not equal, that tells me that the limit as x goes to 1 does not exist, because these don't match. Okay, so the limit does not exist, one of my three conditions failed, immediately I say, well, the function is not continuous. Is not continuous. I'm not yelling, but I'll write in capital letters. At x equals 1. So you just need one to fail and the function then is not continuous. And you see, I could have seen it. I cannot draw it in one single stroke. I have to lift my pen and move down and then continue to draw it. So that is a more intuitive way of seeing continuity. But you do need to see that your three conditions are satisfied, or you need to check those whenever I'm asking for continuity. So what about this one? Well, again, limit from the left as x goes to 1 seems to be positive 1, and the limit from the right also seems to be positive 1. So the limit as f of x as x goes to 1 is equal to 1. So that's good. Is defined. But now f does not take the value of 1. F is defined, but f is taking the value of 2. So condition 1, that f is defined, is satisfied, but now f of 1, oh, sorry, I made a mistake here. This should have been a 1. We're talking about x equals 1. There we go. So f at 1 is not the same as the limit as x goes to 1 of f of x. So here is the third condition for continuity that fails. So since one of them fails, the function is not continuous. So f is not continuous at that point at x equals 1. All right. So I don't need to necessarily show you the graph. I could give you the graph of the function just written out like this. So for example, here, what do you do? Well, is the function defined at x equals 4? Well, you look at your definition of f, and you see that f at 4 is equal to, well, you grab this expression, negative 4 plus 7, which is 3. Okay, it's defined. Perfect. So condition 1 is satisfied. Condition 2. Does the limit exist? Well, to find out if the limit exists, I have to find out the limit from the left and from the right, because this is a pointwise defined function. So on either side of x equals 4, I have different expressions. So from the left, I'd be grabbing the x's that are smaller than 4. So I grab that expression. So that would be the limit as x goes to 4. And my expression becomes a half of x plus 1, and I evaluate it. That gives me 2 plus 1, 3. So far so good. The limit as x goes to 4 from the right, well, I evaluate the other expression when x is greater or equal than 4, and that would be the limit as x goes to 4 of negative x plus 7, which then gives me, I plug in 4, gives me negative 4 plus 7 is 3. So from this, I can conclude, since the two one-sided limits match, that the limit itself, as x goes to 4, is equal to 3, which at the same time also gives me condition 3, that the function at 4 is equal to the limit at 4, as x goes to 4, of f of x. So therefore, the answer is yes, the function is continuous at x equals 4. One last little note. If I would have slightly modified my function and removed the equal sign, then would the function be continuous? It's the same functions, the limits are the same, but now the only difference would be f at 4. Well, you cannot evaluate it here, and you cannot evaluate it here, so f of 4 is not defined. So it's as simple as that. F is not continuous. So a little modification and then continuity failed. Anyways, sorry that this video was a little longer than usual, but I needed to go through all these examples. All right, this is it for section 1.2, and that's actually the end of the module. So you guys have homework for this section, and whenever you need uh, assistance, you can either come to my online office hours or the online session we have, and or you can send me an email or write your questions in the comment if you're not in the class. Thank you so much for watching, and until next time.